Hello there and welcome back to the Science Sleepy Minds. Tonight, you're not just watching stars, you're flirting with them. Above your head, the sky folds in slow motion. You're floating just outside something so dense, so heavy, so absurd that even light can't escape it. The stars stretch and swirl like spilled ink across glass. Your body is weightless, but not free. There's a pull, a whisper of gravity deeper than instinct, like a cosmic undertow urging you closer. You're at the edge of a black hole. Time itself is different here. It doesn't just tick, it slouches, it stretches, it stares back. You probably won't survive this. But if you did, you might just find yourself in the future. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And I'd love to know, where are you listening from and what time is it there? Drop your city and local time in the comments below. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You ease into orbit around the monster, an invisible sphere of gravity with no surface and no mercy. This black hole doesn't glow, but its edges shimmer with tortured starlight, bent in ways your brain can't quite trust. The rest of the universe is out there, distant, buzzing, old. But in here, in this orbit, time feels slower, and it is. As your spacecraft drifts closer to the event horizon, yes, that infamous one-way exit where even photons can't reverse course, you begin to feel it. Not physically, of course. Your watch still ticks once per second, your heart still thumps with its stubborn rhythm. But outside, the universe is changing, rapidly. Your Earth, far away, is racing ahead without you. And here's the big, beautiful, brain-wrinkling truth. From their perspective, you're aging in slow motion. Orbiting a black hole does more than challenge gravity. It changes how time flows around you. You're not violating any laws. You're not tearing a hole in space-time. You're just riding its deepest curve, like skating down the inner edge of a cosmic teacup. This idea isn't science fiction. It's written straight into Einstein's theory of general relativity. Big masses bend space-time, and time flows differently depending on where you are in that bend. The heavier the object, the slower time moves near it. And nothing is heavier or bends space harder than a black hole. Now you might ask, how close is too close? Good question, and it depends on the type of black hole. A small stellar mass black hole, say 5 to 20 times the mass of our Sun, would turn you into linguine before you could even shout, "Wait, was that spaghetti?" Tidal forces near its event horizon are brutal. Your feet and your head would experience such different gravitational pulls that you'd stretch out like a gummy worm left on a radiator. That's what physicists charmingly call spaghettification. But you, smart traveller, you've chosen a supermassive black hole, one like Sagittarius A star, the gentle but ominous beast at the centre of our galaxy. Or better yet, the fictional, but very scientifically informed, Gargantua from the film Interstellar. These are millions, or even billions, of solar masses. They're so big that their event horizons are far from the crushing tidal zones. You could, in theory, orbit just outside one, and survive, and skip ahead. Time dilation near these giants isn't just poetic, it's measurable. Remember in Interstellar, when an hour on the water world cost the crew 7 years outside? That's a real consequence of orbital time dilation near a massive spinning black hole. And yes, physicists helped write that script. Kip Thorne, a Nobel-winning astrophysicist, made sure they got the math as close to right as Hollywood dared. Now, let's put you back in that orbit. You're floating near the edge, watching stars whirl past like streaks on an old VHS tape. From your point of view, everything feels normal. But back on Earth, time is sprinting. You send a message home every hour, they reply every decade. You don't feel the lag, but you see it. News updates become stranger, faster. The slang changes. Fashion becomes unbearable. Humanity ages, but you don't. It's unsettling, but oddly peaceful. You're like a passenger on a train that never stops, watching the world flicker by outside, and maybe, just maybe, someone's watching you too. Historians still argue whether the earliest mentions of time dilation belong to science fiction or obscure physics journals from the early 20th century. But the concept took off when Einstein published his work on relativity in 1915. That's when time stopped being a constant and started behaving like jelly. a jelly influenced by gravity and motion, a jelly you're currently swimming through. There's an odd fringe theory floating in the murkier corners of physics forums, that somewhere out there, civilizations have mastered time dilation orbiting. Not wormholes, not paradox loops, just close, stable orbits near supermassive black holes where their own subjective time crawls, while the universe whirls forward. Maybe that's how they outweight their problems. Maybe that's why they never answer our signals. They're still receiving our first one. And hey, speaking of fringe facts, did you know ancient Egyptians may have had a rough sense of relativistic effects? Not from math, but from astronomy. Their observations of star movements at different altitudes hinted at time-based discrepancies. Was it intuition, coincidence, or just sand-induced mirages? Historians still debate that too. All you know is this: you're now living the slowest second of your life. Each moment stretches. The stars smear into arcs. The glow of the universe grows older with every lap you take, and you're still there, unchanged, untouched. At least for now, because the deeper you get into this orbit, the stranger things will become. Gravity isn't just pulling, it's folding time beneath your feet, and while you think you're hovering calmly in space, Earth has already moved on. It's been a while since you've seen a proper sunrise. Out here, orbiting the gravity well of doom, night and day mean nothing. There is no horizon, only the deep curving shadow of a black hole, swallowing background starlight like it's sipping on soup, and still, somehow you're not afraid. You're just stretched thin between two thoughts. How did time get so weird, and why does it feel like you're standing still while everything else hurries past? To figure this out, you'll have to thank one very frizzy-haired genius, Albert Einstein. In 1915, with his general theory of relativity, Einstein did more than rearrange equations. He rewrote reality. Gravity, he said, isn't a force. It's the shape of space-time itself. The more mass something has, the more it curves the space-time around it. Planets move not because they're being pulled, but because they're following curves, like marbles spiraling down a trampoline where someone very heavy is sitting in the middle. And when space-time curves, time bends with it. It slows down, quietly, obediently. The closer you get to a massive object, the slower time passes for you compared to someone farther away. It sounds abstract, but you've already seen it in action, back on Earth. Did you know that clocks at sea level tick more slowly than those on a mountain? Not by much, but the difference exists. You'd age ever so slightly faster living at altitude. So yes, technically hikers are time travellers. But orbiting a black hole, that's not just a trickle, it's a waterfall. Einstein's equations predict this with alarming precision. The Schwarzschild metric, yes, you can forget that word right after this, describes the geometry of space-time around a non-rotating black hole, and hidden in that dense forest of Greek letters is a brutal fact. The closer your orbit to the event horizon, the more time slows for you relative to the outside universe. This isn't a maybe, it's baked into the laws of physics, and it means that right now, as you coast just above the black hole's surface, you're experiencing minutes, while the galaxy spins through decades. But hang on, you might be wondering if Einstein figured this out over 100 years ago, did anyone believe him? Surprisingly, not everyone. Historians still argue whether Einstein's early supporters truly understood the implications of his work, or if they just nodded politely and went back to Newtonian comfort zones. For decades, relativity was more of a math playground than a practical tool, until technology caught up. One of the first real-world confirmations came during an experiment in 1976, when NASA launched a hydrogen master clock on a suborbital rocket. The result? It ticked faster than identical clocks on Earth, just as Einstein predicted due to the lower gravity at altitude. From that point on, the idea that time is flexible, malleable under gravity, was no longer just blackboard scribbles. It was measurable, and more importantly, it was inescapable. You orbit the black hole now with a calm, eerie awareness. You're not being crushed, you're not screaming toward doom, you're simply waiting, orbiting, letting time run ahead while you lag behind like a child dragging their feet on the last day of school. And here's where things get personal. Let's say you've been circling for what feels like an hour. That's 60 minutes of chewing your protein bar and watching distorted starlight dance in strange curves. But when you check in with mission control, wherever they may be, it's been 6 years. 6 whole years of Earth birthdays, elections, failed TV reboots, and mediocre fashion trends you'll never understand. This is time dilation in action. You don't feel any different. But your atoms, your life, are out of sync with the rest of humanity. And it all goes back to Einstein's core insight. The laws of physics are the same for all observers, but measurements of time and space are not. Time isn't a universal heartbeat. It's local. It's tangled up in your frame of reference. This is why your humble little ship's computer is having a minor existential crisis trying to align its internal clock with Earth Standard Time. From your vantage point, Earth seems to be fast-forwarding like someone held the remote button too long. But to people on Earth, you seem to be suspended in slow motion, like a mosquito trapped in honey. It's not just gravity that does this. Speed plays a part too. Special relativity, Einstein's earlier contribution from 1905, tells us that moving quickly through space slows your movement through time. So if you wanted to double down on time travel effects, you could whip your ship around the black hole at a ridiculous fraction of the speed of light. Would that be dangerous? Absolutely. But so is forgetting your spacesuit zipper, one fringe theory. There's speculation among theoretical physicists that if you found a way to stay in a stable orbit at just the right distance from the event horizon, what's sometimes called the photon sphere, you could experience thousands of years outside in what feels like mere minutes. But maintaining that orbit? Near impossible. One wrong twitch, and you fall in. Forever. Still, people have tried to visualize what that kind of future jump would look like. In one quirky piece of fan science fiction, probably written at 3 a.m, a character returns from a black hole orbit to find their own language has gone extinct, their hometown is a museum, and their favourite snack, cheese-flavoured anything, has been banned for health reasons. You know, the real tragedies of time travel. Back in the physical world, there are still debates about how far this can be pushed. Some scholars argue whether it's theoretically possible to build massive orbital habitats around black holes, purely for time dilation purposes. Others question whether quantum mechanics throws a wrench into the whole elegant system. But as you float there, watching the black hole's edge boil with distorted photons, the philosophical hits you harder than the physics. You aren't really moving through time faster, you're just resisting its flow. You're the rock in the river, not the boat. And when you leave, if you ever do, you'll see just how fast that river's rushed on without you. You squint at the viewfinder and something feels off. Not wrong exactly, just wrong in a quiet, eerie, how long have I been here sort of way. Stars once familiar have shifted, their light smeared into rings by the black hole's gravity. You check the internal chronometer, 1 hour since your last reading. But something about the galaxies beyond suggests it's been far more than that. Welcome to time dilation, or as your ship's I cheekily calls it, tick-tock in slow-mo. Now, we already dipped our toes into the idea, gravity slows time, and the stronger the gravity, the slower the tick. But let's really dig in, because this is the engine behind your voyage into the future, and the weirder it gets, the more it makes perfect sense. Here's a cozy thought. Time is not universal. It doesn't pass the same for everyone, everywhere. And when you're close to something massive, say a black hole, the rate at which time flows can plummet compared to observers far away. That's not metaphor, that's math. Let's simplify for bedtime brain. Imagine you're in a tiny ship orbiting just above the event horizon of a supermassive black hole. Let's call it Chonka, because it sounds less terrifying than Gravity Demon. At this distance, every minute for you could mean 10, 20, even 1,000 minutes out there in the wider universe depending on your exact orbit. And you feel none of it. Inside your ship, your body functions normally. You're not frozen or slowed down. Your biological processes, heartbeats, breathing, digestion of yet another freeze-dried meal, all happen at their usual pace. But relative to the outside universe, you're moving through time like molasses sliding uphill. Now for the juicy part, this isn't just about gravity. Motion plays a huge role too. The faster you go, the slower your time moves compared to someone standing still. That's why orbiting a black hole is a double whammy, extreme gravity and high speed. This is why the International Space Station crew ages just a little slower than we do. It's tiny but measurable, about 0.007 seconds per 6 months. Congratulations, astronauts. You're technically younger than you would have been otherwise. Just don't spend that time all in one place. Historians still debate when the public truly grasped this. Was it Einstein's moment in 1915? Was it later, during the first GPS tests that had to compensate for relativistic effects to get directions right? Or was it 2014, when Interstellar made people sob into popcorn while a dad missed 23 years of his daughter's life in one scene? Either way, the science is solid. Clocks tick slower in a strong gravity or at high velocity, and the closer you are to a black hole, the deeper you fall into the curve of space-time, and the more you feel time differently. Well, you don't feel it, they do. Here's a fun fringe experiment. Imagine two identical twins. You stick one in orbit around Chonka, and you leave the other back on Earth, probably watching reruns and worrying about climate change. You let black hole twin orbit for, say, a week. When they come back, they've aged a week. Earth twin, a decade older. And now their whole relationship is ruined because Earth twin is into smooth jazz and complains about kids these days. This is a dramatized version of the twin paradox, which we'll go full throttle on later. But even in this sleepy state, it's nice to imagine that simply changing where you are and how fast you move can totally warp your experience of time. Now let's head back to your cozy orbit. Around you, radiation flickers from the accretion disk, a whirl of superheated particles spiraling toward doom. It's not bright, not like in cartoons. It's unsettling. Like watching a whirlpool made of fireflies. You can't hear it, but your ship's sensors hum with warnings. This much energy warps space, and in warping space, it alters time, and that's the real kicker. You're not moving into the future like Doctor Who in a phone box. You're simply experiencing less time while the rest of the universe keeps ticking. You're in the slow lane of time's highway, letting everything else zip past you. A lesser-known historical tidbit. In the 1960s, during early Soviet spaceflight experiments, there was speculation, half in jest, about putting highly precise clocks on cosmonauts to see if the relativistic effects would be noticeable. At the time, our tech wasn't sensitive enough, but later tests proved it. Time dilation happens, even at low speeds and gravity. The universe does not run on one master clock. There's even a lovely fringe theory by some theoretical physicists. Time might not flow at all. It might just be a static dimension, like space. The sensation of time passing could be your brain's way of processing change, not an actual cosmic phenomenon. Wild, right? It's like finding out the river you thought you were drifting on is actually a frozen sculpture, and your consciousness is the only thing moving. Still, as comforting as that is, your senses insist you are, indeed, aging slower than the rest of humanity. The gravity of the black hole compresses not just time, but your timeline. Your personal clock has gone rogue, stretching out seconds while distant stars zip through centuries. One could even argue, philosophically, that you're watching the future arrive, one slowed heartbeat at a time. What makes it all real, not just theory, is that you can measure it. Time dilation isn't some abstract weirdness. It's the reason your ship's internal systems have to constantly correct for orbital drift. Your nav computer runs two clocks, one for you and one for the rest of the universe. They disagree. A lot. But only one of them gets to send emails to Earth. And now Earth writes back in awkward tones. The team you launched with is long gone. Your niece runs the space agency now, and she's asking if you'd like to return. There's a museum exhibit dedicated to your ship. Children leave sticky-fingered drawings in your honor, but you're just floating, existing, not trapped, not lost, just slowly skipping over the pages of a very long book. You haven't traveled to the future in a spaceship. You've just let time rush past you while you sat still. You reach for the little screen embedded in your control panel. It's scuffed from use. Maybe from that time you dropped a spoon during turbulence, or maybe from the incident with the experimental zero-G soup. Either way, it's still running. And on it, a slow, steady data stream ticks along. Velocity, radiation levels, orbital position, and one very peculiar number. Your ship's computer is constantly adjusting for time discrepancy, because believe it or not, without doing so, even your onboard GPS would be hopelessly lost. That's right. The same time dilation you're experiencing on the grand scale around a black hole, it's happening back home too, quietly, persistently. Every second of every day, satellites in Earth orbit are ticking just a little bit faster than clocks on the surface. How much faster? About 38 microseconds per day. Laughably tiny? Yes. But if you're trying to use a GPS system that relies on triangulating signals from satellites to pinpoint your position, even the tiniest time error grows quickly. After a day or two, your phone could think you're in a different town. After a week, you're floating somewhere in the Pacific, ordering a latte for a seagull. So how do engineers fix that? They bake relativity into the system. Every single satellite in Earth's GPS constellation is calibrated with Einstein's equations. They account for both general relativity, because the satellites are higher up in a weaker gravitational field, and special relativity, because they are moving fast and thus experience time slightly more slowly. These opposing effects don't cancel out perfectly, so corrections are made constantly. And it works. Every time you ask your phone for directions and it tells you to turn left into a Starbucks parking lot instead of the Hudson River, you're benefiting from a theory that once sounded like science fiction. Historians still argue whether the military initially believed the GPS system needed relativity corrections at all. There's a charming rumour that some early engineers thought they could turn relativity off, and only later realised their error when satellites began reporting nonsense. Whether that's true or just delightful nerd folklore, we may never know, but the fact remains, even modest gravity bends time, and yet, it's child's play compared to where you are now. Your orbit around the black hole is an exaggerated opera-level version of GPS relativity. Instead of microseconds, you're seeing years pass by in what feels like moments, and instead of a helpful Google Maps ping, you're dealing with mission updates that now arrive decades apart, sometimes delivered by the great-great-grandchildren of your original crew. Their messages always start the same. We're still here, still watching. You can't reply quickly enough. Your signals arrive like postcards from deep time. Back in your cozy, pressurized cabin, the idea is settling in. This isn't just theoretical. It's not a gimmick. Every second you spend here is future time skipped. You've become a living demonstration of the same principle that makes GPS work. It's just dialed up to 11. There's something funny about that, isn't there? You embarked on one of the most ambitious gravitational experiments in human history, and the core concept is the same as your phone trying to find the nearest gas station. Science is humble like that. Majestic and mundane, all at once. And speaking of mundane, ever wonder who first measured time with enough precision to make any of this possible? Here's your mainstream history fact of the night. In the 1960s, the development of the atomic clock gave us timekeeping accurate enough to test relativity directly. The Effield-Keating experiment in 1971 flew atomic clocks on commercial airliners around the world and then compared them to synchronized clocks on the ground. The result? Exactly what Einstein predicted. Time passed differently for the flying clocks. Weirdly, those clocks were kind of like you now, just moving through a distorted version of time, thanks to velocity and altitude. You're basically the VIP version of the Haffel-Keating clocks. Just, with less legroom and a better soundtrack. As you circle the black hole once again, you glance at the readout. The orbit takes 55 minutes from your point of view, but somewhere out in the wider universe, months are passing. Seasons, solar flares, governments, empires rising and falling, fashion cycles you'll never understand, TikTok dances you'll never attempt. This isn't time travel the way science fiction usually portrays it. No flux capacitors, no mysterious doors or steampunk portals. You're not skipping through time. You're letting time speed ahead, around you, without you. You sip water from your ship's recycler. Still cold, still recycled sadly, still hydrating. The ship hums softly, its systems synced to your frame of time. Out there, the stars twist on fast forward, but in here, the music plays slow, and then there's a tiny ping on the comms. Another message, another future. This one's from a language assistant AI that doesn't sound familiar. It apologizes for the latency, sends a packet of data including holographic news, and addresses you as the orbiting one. Apparently you're a cultural icon now. There's a new festival named after your ship. Children dress up as you and spin in circles laughing. One even wrote a poem. Time stands still around the hole, but stars have danced and paid the toll. The traveller watches, never old, while galaxies grow dark and cold. Fringe? Yes. Slightly unsettling? Also yes. You lean back. The stars wheel again. You've given up trying to count the orbits now. And just like with GPS, the world outside continues to refine its own sense of now, even as your now stretches like taffy. Time, it turns out, is elastic. You are the proof. You float quietly in your orbit, wrapped in the curved arms of space-time like a hammock slung too close to the sun. Outside your window, light bends unnaturally. Stars elongate into arcs, and galaxies spiral like they're painted on some rippling oil surface. It's haunting, yes, but strangely familiar too, especially if you've seen Interstellar, and if you haven't, well, you should. Not just for the father-daughter heartbreak or the cornfield chasing drones, but for one specific star of the show, Gargantua, the black hole so terrifyingly accurate that even physicists gave it a slow clap. See, Interstellar didn't just invent a cool black hole to look dramatic. They built one using actual physics. Literally. Kip Thorne, the Nobel Prize-winning physicist who served as a scientific advisor and part-time reality check on the film, collaborated with the visual effects team to model how light would behave near a rotating supermassive black hole. What they came up with wasn't some flat circle or evil abyss. It was a glowing halo of warped light, a gravitational lens twisting space so fiercely it wrapped starlight around the entire object like a shimmering cosmic crown. And here's the part that'll twist your perception. The movie's depiction was so accurate, scientific papers were published based on it. That's right. Hollywood accidentally helped science. The math was real. The time dilation? Also real. Remember the now infamous scene where the team lands on a water-covered planet, only to return to the ship and find that 23 years have passed for their colleague, while only a few hours ticked by on the surface? That's not just cinematic drama. That's exactly the kind of future-leaping effect your orbit is pulling off right now. In the movie, the time discrepancy was extreme because the planet orbited extremely close to Gargantua's event horizon, where gravity was immense and relentless. Kip Thorne worked out the numbers. For 1 hour to equal 7 Earth years, the planet would need to orbit within about 1.7 gravitational radii of the black hole, and the black hole itself would need to be spinning at nearly the maximum possible rate. Do those numbers seem cartoonishly specific? They are, but they're also real. And here's your mainstream history moment. Interstellar wasn't the first time pop culture explored time dilation near black holes, but it was the first time it did it right. Prior attempts were less precise. Think, the ship got sucked into a time vortex and now they're evil clones. Not quite the same vibe. The idea of time warping near black holes has been around since the early 20th century, shortly after Karl Schwarzschild, yes, that name again, used Einstein's equations to describe the space-time around a spherical mass. But for decades the math was just that, math. No one thought we'd see it. And yet, now, astronomers with fancy arrays of telescopes like the Event Horizon Telescope have captured images of real black hole shadows. The famous 2019 picture of M87 star, the Donut of Doom, showed us the glow of material spiraling toward the event horizon, bent by gravity into a perfect halo. Kind of like Gargantua, kind of like the black hole you're orbiting now. And that brings us to something fascinating. Your orbit isn't just a physics experiment. It's a cinematic moment made real. The same equations that made audiences cry into their popcorn are now the laws dictating how you stretch your minutes into decades. Fringe fact for the night. Some physicists speculate that a version of Gargantua could be out there for real. The universe is vast, and supermassive black holes spinning near the speed limit of light aren't just possible, they're likely. Sagittarius A star, the one at the centre of our galaxy, may not be spinning quite fast enough, but others, like Cygnus X1, have spin rates pushing the extreme. If one of them has a near-horizon planet, well, time would get very weird down there. Your ship hums gently, systems recalibrating again for the endless slipstream of relativistic drift. The black hole below you might not be Gargantua in name, but in physics. Oh, it's close. The light curves, the orbit tightens, and your sensors flash occasional warnings about minor radiation flares from the accretion disk. Nothing dangerous. Yet. But here's something very human. You're getting used to it. The warped stars, the sluggish time, even the silence between transmissions. You've become part of the clockwork now, a gear that turns too slowly to see but keeps ticking anyway. And when Earth sends another message, you feel the weight of it. The awe, the melancholy, the curiosity. You're a legend to them. A living thought experiment. An echo of a science movie they now teach in schools. Historians still argue whether Interstellar helped popularize real physics, or just inspired a new generation of people to say time is fake at dinner parties. But in your case, it did something else. It foreshadowed your journey. Maybe that's why you brought the film with you on your ship's entertainment drive. You've watched it more than once now. You fast forward through the corn, you pause during the orbit, you stare at that planet. and now you know exactly what it feels like to wait for years to pass in seconds. There's one scene you keep rewatching, the one where Murph, the daughter, sends a message after decades. She's older than her father now. Her voice trembles. And he hasn't aged a day. It hits different when you are the one who stayed young. And yet, strangely, there's no sadness here, just quiet awe. Because you're not cheating time. You're letting it move on like wind in the trees. You're not skipping ahead. You're orbiting through eternity 1 second at a time. You adjust your seatbelt, not because there's turbulence, but because habits don't keep track of time dilation. Somewhere, decades have passed. You've eaten maybe half a granola bar. And here's the thing you can't shake. This isn't magic. This isn't sci-fi technobabble. This is you, time traveling, by doing absolutely nothing. You're not moving through a wormhole or being zapped by lightning. You're not clutching a glowing watch or riding shotgun in a DeLorean. You're just sitting, orbiting, hanging out a whisper away from the most gravitationally intense object in the known universe. And while you do that, the future happens without you. Back on Earth, your name has slipped into textbooks and bedtime stories. You're the observer, the sleeper, the one who waits. Some say you're still in orbit. Others say your ship must have been torn apart long ago. There's even a cult that lights candles every year on the anniversary of your departure and live streams a 24-hour countdown, just in case today's the day you finally return. You haven't aged, you haven't noticed. To you, the journey's barely begun. So let's get clinical for a second. How exactly are you experiencing time? What does it mean to be a time traveler in this context? Well, let's do a little thought experiment. You decide to orbit this black hole for what feels like 1 year. That's 365 ship days. You celebrate your space birthday, eat a rehydrated cupcake, and mark a notch in the wall like a prisoner of relativity. Meanwhile, out there, 50 years pass, or maybe 200. Depends on how tight your orbit is, how fast you're moving, and how close you are to the event horizon. When you finally pull away and head home, you're essentially stepping into the future. You've skipped forward, not by changing the laws of time, but by sitting still where time moves differently. That's the sneaky truth about this flavor of time travel. You don't move through time. You let time move around you. It's like waiting under a rock while a hurricane rips across the landscape. When you crawl out, everything's changed. Now let's not sugarcoat it. This method has limits. You can't go back. There's no rewind button on the black hole, no reset. Once you've skipped ahead, you've skipped ahead. And let's be honest, that makes for a lonely kind of superpower. You might return home to a world where no one remembers VHS tapes, where all dogs are genetically engineered to be hypoallergenic, and where the phrase, "go touch some grass," is literal because everyone's in VR. And you're the relic. Not dusty or grey, but outdated in subtler, sadder ways. Physicists actually have a term for your situation: differential aging. Your body has aged less than the people you left behind. But aging here isn't just about wrinkles or back pain. It's about context. Everyone you knew is gone, or different, or so impossibly updated that you can't hold a conversation without subtitles. Still, let's be clear, you've done it. You've travelled to the future, no paradoxes, no explosions, no temporal police kicking in your airlock, just the quiet, lawful elegance of Einstein's equations, unrolling space-time like a carpet and letting you take a shortcut, simply by waiting. Now, a quick quirky fact for your thoughts. In the 1970s, there was a proposal, completely serious, to put a human in low Earth orbit for decades, purely to study the effects of time dilation and biological aging in extreme isolation. It was eventually scrapped for being, well, horrifyingly expensive and ethically questionable. But the idea lingered. Because there's always been something alluring about sitting still while the world races forward. Even ancient myths played with it. In Japanese folklore, the story of Urashima Taro tells of a fisherman who visits an undersea palace for a few days and returns to find centuries have passed. He hasn't aged, but the world is no longer his. Historians still debate whether such myths are primitive explorations of time dilation, or just moral warnings about leaving your home for too long. But here you are, living proof that those old stories weren't entirely wrong. And here's something else to stir your sleepy neurons. What would happen if you chose to stay? Really stay? For centuries? For millennia? Until the Milky Way looks different? Until Earth's continents have shifted? until the sun begins its slow bloat into a red giant and the oceans boil away. Would you eventually feel detached from human identity? Would you care? Or would you become something else? A biological witness to the future, a memory capsule in orbit, a relic with a pulse. There's a poetic cruelty in that, isn't there? You wanted to see the future, but the future isn't always something you arrive at. Sometimes it's what happens after you're gone, and yet somehow you've threaded the needle. You've made it to tomorrow while still being very much alive. You're not just observing time dilation anymore, you are the dilation. Still, the ship's systems were built with an exit plan. Your engines can pull you free when you're ready. Your trajectory can be recalculated. Your return to Earth, if that's even what it's called anymore, is possible. You just have to want it. But maybe not yet. Maybe one more orbit, one more year, one more spin of the stars before you return to a world so different, so distant, it might as well be an alien planet. Maybe you're not ready to face the consequences of being the future traveller. Because while it's easy to imagine skipping ahead, it's harder to imagine not belonging when you get there. The black hole looms below like an open eye, unblinking, unknowable, pulling at everything, even time itself. And now, as your ship stabilizes into a tighter orbit, it's time to talk about the real MVP of your journey into the future, the perfect black hole. Not all black holes are created equal. Some are angry little monsters barely a few times the mass of the sun, spinning fast and slurping gas like space smoothies. Others are ancient, bloated giants, supermassive black holes that sit calmly at the centres of galaxies like cosmic librarians, so massive that entire star systems could fall into their gravitational embrace without a ripple. For our sleepy science purposes, you want the second type. You want a black hole so large, so chill and so stable, it lets you orbit dangerously close without getting turned into human string cheese. Let's meet your ideal host, a supermassive spinning black hole. Not just any black hole, a Kerr black hole. That's the name physicists give to rotating black holes, which are dramatically different from their non-spinning cousins. Discovered mathematically by Roy Kerr in 1963, these beasts don't just bend space and time, they twist it, dragging space-time around like a cosmic whirlpool. This effect is called frame dragging, and yes, it's as weird as it sounds. Near a rotating black hole, space-time itself is pulled along with the spin, like honey around a spinning spoon. Objects caught in this flow are forced to orbit even if they don't want to. That's right, you don't need fuel. You're stuck in the swirl, and this twisty situation has a bonus. Spinning black holes give you more room to maneuver. Unlike a non-rotating Schwarzschild black hole, which has a hard do not cross event horizon, a Kerr black hole lets you get closer, much closer, without getting sucked in. The faster it spins, the closer you can get. Remember Gargantua from Interstellar? That fictional black hole wasn't just spinning fast, it was spinning at nearly 100% of the theoretical limit. That's why the water world could exist so close to the event horizon without being obliterated. Historians still argue whether real black holes can spin that fast. Observational data from X-ray binaries and accretion disks suggests some are getting very close, but hitting the true speed limit would require very specific and unlikely conditions. Still, even at 90% of the max spin, you'd see outrageous time dilation. Now you might be thinking, how big is big enough? Well, let's take Sagittarius A star, the supermassive black hole at the centre of our own galaxy. It's around 4 million times the mass of the Sun. A black hole that size has an event horizon about 12 million kilometres across. That's roughly the diameter of Mercury's orbit. Massive, yes. But Sagittarius A star is a little too quiet. Not much accretion, not much spin, not ideal for extreme time dilation tourism. Instead, you'd want something like TON 618, a real, utterly ridiculous black hole estimated at 66 billion solar masses. Yes, billion with a B. Its event horizon would stretch well beyond the orbit of Pluto. You could comfortably fit entire planetary systems inside its borders and still have room for a snack. Orbiting a beast like that, especially near the edge of the photon sphere, the zone where light itself can orbit, you could slow your experience of time dramatically. Decades could pass for you while thousands of years unfold in the outside universe, all without ever crossing the event horizon. But let's not forget, just because it's big doesn't mean it's safe. Even the most relaxed supermassive black hole still throws off intense radiation, wild gravitational shears, and the occasional relativistic jet, aka a beam of pure doom moving at near light speed. That's why picking your black hole is only half the equation. The other half is how you orbit it. Here's where things get precise. You can't just wing it. You need a stable orbit at the innermost stable circular orbit, or ISCO, which, yes, is a real and very awkward acronym. The ISCO marks the closest distance you can orbit a black hole without spiraling in forever. The radius of the ISCO depends on the black hole's spin. For a non-rotating one, it's about 3 times the Schwarzschild radius. For a maximally spinning black hole, you can get right up to the edge, just outside the event horizon. And that's where the magic happens. The time dilation at ISCO is intense. It's where gravity's grip on time becomes absurd. Every second you spend there could equate to hours, years, or centuries elsewhere. You're not just travelling to the future, you're letting it outpace you while you stubbornly tick along in slow-mo. There's a slightly terrifying fringe theory floating around in the physics community. That alien civilizations might build habitats near ISCO orbits, not for energy, but for time control. If they wanted to survive until the end of the universe, they could just wait it out near a black hole. To them, the external universe would race by and fast forward, while their experience slows to a crawl. Would you ever notice them? Probably not. From your perspective, they'd barely age at all. From theirs, you'd be long gone. You float now in a near ISCO orbit around your chosen black hole. The view is both dazzling and disorienting. The stars have gone haywire, distorted, duplicated, lensed into loops. The accretion disk glows faintly in bands of blue and orange, flickering with X-ray heat. And below it all, that dark sphere of no return spinning quietly, warping space-time into a funnel that never ends. You're exactly where you need to be. Not so close that you're lost. Not so far that time flows like it does on Earth. You're riding the knife edge, slow enough to reach the future, fast enough to stay alive. And still, the question lingers. How long do you stay? A week? A year? A century? Do you wait until human civilization has burned itself out, hoping the next species is friendlier and makes better music? Or do you fire your engines, pull away from the curve, and return to a world that will no longer recognize your voice, your face, or your taste in memes? You don't have to decide just yet, not while the black hole keeps whispering. Stay a little longer, just one more orbit. The systems on your ship hum softly, calibrated to a clock no longer synced with anything human. The voice assistant, who once reminded you of hydration schedules and system checks, now speaks in slightly different tones, updated by a patch from engineers long gone. Somewhere back on Earth, assuming Earth is still a relevant term, a whole new software language has probably evolved. Yours is a legacy version, comfortably outdated. And it all hinges on one thing: you didn't fall in. Because here's the secret behind your graceful little leap into the future. You need a ride that can handle the edge without crossing it. So, let's talk shop. Let's talk about the technology that could keep you alive while you flirt with a black hole. Spoiler, it's a little more complicated than slapping some heat shields on a metal can and calling it a day. Let's start with the most basic requirement: surviving the orbit. Orbiting close to a black hole, especially at or near the ISCO, where time dilation becomes most delicious, means being exposed to some serious forces. Gravity is curving space-time like taffy, and if your orbit slips even slightly, you risk spiraling in with all the grace of a confused duck. And once you cross that event horizon, game over. You can't radio for help, you can't reverse engines, you're just gone. So, you need precision thrusters capable of micro-adjustments. You need stabilizing systems that can calculate tidal forces in real time, and apply tiny corrective nudges to keep you floating on the razor's edge. That's not sci-fi fluff. Real spacecraft today already use tiny ion thrusters to make course corrections over vast distances, just not at relativistic death trap speeds. Then there's radiation shielding. Black holes don't just sit there being mysterious. They're often surrounded by accretion disks, which are hot, chaotic, plasma-filled rings of doom. As matter spirals in, it heats up, sometimes to millions of degrees, spewing out X-rays and gamma radiation. That's not great for your skin, or your DNA, or the ship's wiring. So to orbit safely, your craft needs to be wrapped in radiation protection. Probably a combination of layered polymers, liquid hydrogen tanks, and maybe even an active electromagnetic field. Yes, like a force field, though the real kind, not the Star Trek kind. Scientists are seriously exploring electromagnetic shielding to deflect charged particles for future Mars missions, and you'd need a supercharged version of that to survive here. But even with the right shielding, there's another threat: spaghettification. That delightful term refers to the tidal forces that can stretch your body into a very, very long noodle if you get too close to a small black hole. Luckily, as we've discussed, supermassive black holes are actually more gentle at their edges. Their gravitational gradient, the difference in pull between your head and your feet, is low enough that you wouldn't feel a thing. Still, that's assuming you don't fall in. That's the deal breaker, always. So your ship needs one more thing: a robust navigation AI, one capable of performing instant relativistic calculations, keeping track of gravitational distortions, and adapting to frame-dragging effects on the fly. Because remember, near a spinning black hole, even space-time itself is rotating. And if you don't account for that, you'll drift, you'll slip. And if you slip, you spiral. And if you spiral, well, you know how that ends. Fringe theorists, ever the overachievers, have proposed theoretical black hole sails. These would be gigantic, ultra-thin structures capable of riding the energy gradients around black holes, using radiation pressure to maintain position. Think solar sails, but on cosmic steroids. Could you, in theory, hover just outside the event horizon using nothing but light pressure and careful calibration? Probably not. But maybe. Historians still argue whether those ideas were beautiful nonsense or overlooked genius. But let's say you've got your ship. Your shielding is solid. Your thrusters are whispering out micropulses. Your AI is humming lullabies made of math. Now comes the final element: clock management. Because from your point of view, your clocks tick normally. Your watch says 2:17 p.m. You take a nap, you wake up, it says 3:05 p.m, but the rest of the universe is leaping ahead in fast forward. So your onboard systems must track two clocks at once. 1. Local time, the subjective experience inside the ship based on internal processes and biological rhythms. 2. Universal time, a calculation of what time it is in reference to an observer far outside the black hole's influence. You might call it Earth relative time, though by now Earth might just be a museum with good snacks. Managing these clocks isn't just a novelty, it's critical. If you ever plan to return, and we'll talk more about that grim little decision later, you need to know how far ahead you've skipped. Otherwise, you might show up at Earth's doorstep during an ice age, or a robot uprising, or worse, a time when real food is considered outdated. Your ship keeps track for you, of course. The software updates every orbit. It tells you the difference between your time and the external universe's time down to the nanosecond. And as of now, you've skipped 62 years, you've aged 6 months, you still look like someone from the 2020s. The universe does not. And this really is what defines you now. You're a future traveller not because of where you're going, but because of how differently you experience going there. Time isn't a road for you, it's a sea. And you've found the part where the current slows down just enough to float while the tide of the cosmos surges past. There's an irony, isn't there? You've built a miracle of engineering, a machine that can defy time's normal rhythm, a system that lets you orbit death itself and come out the other side alive, unchanged, and still. You're alone, orbiting silence, a blip of human curiosity in the shadows of an ancient spinning void. The ship tilts slightly, just a minor course correction, so smooth you almost don't notice it. The stars beyond the window wobble a little, like a reflection on a disturbed pond. Another orbit begins. You check the mission clock. From your point of view, barely an hour has passed. From the outside universe's point of view, 7 years. Congratulations. You've hit the sweet spot, the famous 1-hour orbit that turns minutes into decades. Not theoretically, not metaphorically, actually. Time has stretched so thoroughly beneath your feet that you're barely brushing the present while the rest of the cosmos is already racing through your future. And the best part, you're still technically on schedule. Let's dig into the numbers, because now you've reached the zone where time dilation becomes absolutely unhinged. You're close, very close, to the event horizon of a fast-spinning black hole. Your trajectory has locked you into a narrow ribbon of orbit just outside the danger zone. Here the equations twist and groan, but they still hold. In a Kerr black hole, that is one with angular momentum, space-time itself is dragged along with the spin. This lets you skate the edge more closely than with a non-rotating black hole, and that's where the clock starts to betray your senses. Your physical orbit might last 55 minutes. You could circle this monster 26 times in a standard day. But with time dilating so extremely, each loop forward costs the universe years, decades, centuries, if you tighten the path just a little more. In Interstellar, this concept hit the mainstream, when the crew spent just over an hour on Miller's planet and returned to find 23 Earth years had passed. That wasn't just sci-fi drama, it was Kip Thorne's math in action, and you've reached a similar point. Let's say your orbital velocity is high, around 60% the speed of light. Combine that with the near ISCO position in the warping, frame-dragging soup of curved space-time, and the math starts to look surreal. For every second you feel, the outside universe could experience thousands. You take a sip of recycled tea, Earth experiences another election cycle, you blink, a new alphabet is trending, the ship, ever faithful, tries to keep you updated, you receive compressed news packets from outside the black hole's influence. A lot of the headlines don't make sense anymore. Vertical farming now mandatory. Climate rings successfully stabilise Antarctic weather. Our elected mayor wins again, third term with 98% approval. You stare at the screen like a confused time tourist. You haven't missed just events, you've missed cultural rewrites. And yet, you're calm, because this was always the plan, to orbit, to wait, to slip into the future one moment at a time. But you wouldn't be here if you didn't wonder something crucial. How close can you actually get before the black hole pulls you in? The answer is a dance between mass, spin, and orbital precision. For a maximally spinning Kerr black hole, the ISCO, the innermost stable circular orbit, is only about half the Schwarzschild radius. That's dangerously close. Your ship must calculate exact velocities, gravitational shears, and relativistic corrections constantly to stay afloat in that region. One micro-error, one unexpected push from a stray chunk of matter in the accretion disk, and you'd be inside the ergosphere, where escape becomes, let's say, unlikely. Just outside the event horizon, the ergosphere is the region where space-time is being dragged faster than light. You could still, in theory, escape from there, but only if you're already moving just right. And if you're not, you fall in, and once you cross the event horizon, the conversation ends. No more radio signals, no more orbit corrections, no more you. What happens inside is still hotly debated. Some physicists say you'd be crushed into a point of infinite density, a singularity. Others argue that quantum mechanics might prevent such nonsense from happening, protecting information and preventing true destruction. Historians still argue whether the singularity is a real object or just a failure in our equations. We've never seen one. We've only inferred their existence from gravity's tantrums. But whatever's down there, no one comes back to blog about it. And you have no intention of finding out, which is why your orbit skirts just above danger, balancing on the razor-thin curve of space-time. The gravitational pull is extreme, but stable. The spin of the black hole gives you a kind of gravitational slingshot assist every few orbits, reducing the energy required to maintain your position. The result? You live in a reality where one orbit equals 7 Earth years, 7 years of planetary drift, of political shifts, of languages evolving, of family lines continuing without you. 7 years for everyone else. For you, another half hour. Fringe theory time. Some researchers believe that this kind of time dilation could be used intentionally, not just to visit the future, but to preserve knowledge. If you had something so valuable that it needed to survive the chaos of galactic time, you could lock it in a craft like yours, orbiting a black hole and retrieve it far, far down the line, like a slow-turning vault, a memory satellite adrift in relativistic delay, which begs the question, maybe you're not the first. Maybe someone or something else is orbiting out here too, quiet, still, waiting, not asleep, just passing time differently. You scan occasionally. Your sensors sweep the emptiness for other thermal signatures, signs of engine emissions, even errant debris. So far nothing. But every time you pass through the starlight lens of the black hole's corona, you see strange shapes, mirror images of galaxies, warped copies of light that may be weeks or centuries old. Sometimes they even look like ships. Probably illusions. Probably. The math of this orbit is ironclad. But the experience? That's where things start to stretch. You begin to wonder, what's happening back home? If Earth still exists, have they moved beyond you? Have they evolved, digitized, ascended, downloaded their minds into crystals shaped like owls? You check the onboard time again. 1 hour and change. The universe is now centuries ahead. You're running out of orbit. And yet, you haven't aged a day. You're standing in the mirror. Same face, same tired eyes, same scar from that one kitchen mishap with the dehydrated lasagna tray. Nothing's changed. Except, of course, everything. The clock says it's been just over a year since you began your tight orbit around the black hole. 1 Earth year, measured by your body, your ship, your thoughts. But when you tap into the universal clock, the one maintained by your ship's external reference sensors, calibrated to distant pulses and redshift calculations, you feel the weight of what you've done. It's been 8 decades, 80 years. And that's the moment it sinks in. You can't come back the same. Not because you're broken or damaged or confused. You're still you. Still think like someone from the 2020s. Still hum the same music. Still use slang that probably died out generations ago. But the world no longer matches your rhythm. You're a relic, an antique in running shoes. Pulling out of orbit was always an option. Your ship's return trajectory was pre-programmed before launch. The engines, low thrust, high efficiency fusion drives, can gently lift you from the deep curve of the black hole and send you home. The AI even helpfully displays the optimal window for escape and calculates your ETA back to Earth orbit. And yet, it doesn't feel like a return. It feels like an intrusion. Because once you leave this orbit, once you accelerate away from the time-slipping edge, you rejoin the normal flow of time. From that moment forward, time passes equally for you and the universe again. No more skipping, no more lagging, no more watching history blur past the window like a time-lapse. You hit the thrusters, they whine, you begin your climb. Slowly, achingly slowly, you pull away from the event horizon. The stars begin to look less warped. The background radiation shifts, your velocity changes frame, gravity loosens its grip, and time resumes its usual pace. You're aging in sync now, but the rest of the universe already had a head start. By the time you rejoin Earth's orbit, 132 years will have passed. You age 7 months during the trip. That's it. Everyone you ever knew is gone. Everyone who watched you leave, every scientist who approved the mission, every engineer who built the ship, every neighbor who asked where you were going, is now dust, memory, or a footnote in a classroom. And the planet you return to? It's familiar, but sideways. The continents are the same, the oceans still blue, but everything else is off by just enough to sting. The language is mostly English, but weird. The vowels drifted, some words disappeared. There's a lot of AI syntax embedded into everyday speech now, contracted terms, strange emphasis. Your old accent sounds like Shakespearean theatre to them. Your ship docks at an automated orbital station. You're met by a greeting party, though it's just 4 androids with human eyes and 2 wide smiles. They're kind, courteous, confused. They've never met a baseline human before. You are that rarest of creatures, a time-lost original. And here's the funny part. To them, you're not a time traveller, you're a historical object. They don't celebrate your return, they preserve it. You're interviewed by a council of historians who study the gravity experiments like a religious sect. They ask you what 2025 smelled like, whether birds really sounded the way the simulations suggest. They ask you to describe a car, a tree, a holiday. They give you food that doesn't require chewing. They offer you housing in a museum habitat, a fully recreated early 21st century apartment, complete with replica furniture and something called classic toothpaste. Children visit on weekends and stare at you through polarized glass. They call it the time capsule program. And you feel like a ghost. Historians still argue whether the psychological impact of re-entering society after extreme time dilation is survivable. In theory, the math holds. The traveller arrives intact. But what the equations don't account for is cultural distance. You're not just removed from your own era, you're irrelevant to theirs. Music, politics, ethics, food, sports, all evolved without you. You missed every argument, every movement, every breakthrough. You weren't there when humanity made peace with its machines. You weren't there when they terraformed the moon, or when they cancelled meat, or when oceans began to glow from engineered algae.
They show you a recording of your own launch. They smile, you nod, and then, slowly, you begin to grasp what you've done. You've jumped forward, yes. You've seen the future, but at a cost. You've sacrificed belonging for the privilege of witnessing what comes next. And maybe that's the truest form of time travel. You didn't break time. You respected it. You played by Einstein's rules. You aged slowly in a fast-forward world, and now you're here, older, untouched, and completely out of sync, but still alive. Fringe theorists once speculated that future civilizations might reject time travelers entirely, not out of fear, but out of apathy. What could someone from 2025 possibly understand about the year 2157? Apparently, not much. And yet, a child leaves a note outside your habitat window. It's written by hand, an ancient ritual, apparently. It says, "You look like my grandpa, but you're from the beginning of the world. Did it hurt to miss it?" You read it twice. You write back, "No, it was quiet." Because that's the truth, isn't it? Time travel isn't noisy. It's not clocks whirling or portals flashing. It's silence. Waiting. Watching the world bloom without you. The museum habitat's lights dim on a schedule you can't change. Soft ambient sounds pipe through the walls. Artificial wind. Bird calls sampled from long-dead forests. The distant trickle of a brook that never existed. Someone decided this was what the natural world sounded like in the early 21st century, and you, the time-displaced guest of honor, are expected to find it comforting. You don't mind. It's familiar enough. You still wake up before the lights come on, still dress in old clothes replicated by bioprinters, still make tea in a kettle that isn't really heating water but playing a temperature simulation, all part of the performance. But some mornings, you look at your hands and think, I shouldn't be here. You never meant to come home and find yourself an exhibit. You just wanted to see the future. And yet, as bizarre as your story is, you're not exactly the first. In fact, the first human time travelers weren't orbiting black holes. They were wearing orange suits and peeing in tubes. Their ships weren't built to bend time, but time bent for them anyway. Let's talk about that. Your sleepy brain might perk up to learn that time dilation has already happened in recorded history. Tiny, yes, but measurable. And it happened to astronauts, human beings in low Earth orbit. Take Sergei Avdeyev, for example, a Russian cosmonaut who spent a total of 748 days aboard space stations Mir and later the International Space Station. Due to the combined effects of orbital velocity and gravitational time dilation, his experience of time was slightly slower than ours back on Earth. The difference? About 0.02 seconds. Not exactly a trip to the year 3000, but real, proven. A biological clock ticking just a smidge behind. Then there's Gennady Padalka, who holds the world record for the most cumulative time spent in space, 878 days. He aged a little less than his twin brother back on Earth, just a few milliseconds, barely worth writing home about, unless you're a physicist or someone with a very sensitive stopwatch. And if that still sounds underwhelming, remember, even you experience time dilation today. If you live in a high-rise apartment, your head is aging faster than your feet. Time flows differently at different altitudes. It's not fantasy, it's physics. Which brings us back to you. Here you are, someone who took the same principle and amplified it by several orders of magnitude. You use the same math that applies to GPS satellites and ISS astronauts, but you did it near a black hole. You're the final form of orbital time dilation, the deluxe version. The historians love this connection. They wheel in school groups, children who think the moon landing was vintage, and explain how the observer is part of the continuum. From Yuri Gagarin's first orbit to the first permanent colony on Europa, from space shuttles to singularity skimmers like yours, time has always been the cost of exploration. Sometimes minutes, sometimes centuries. You're part of that story now, whether you like it or not. A fringe museum curator, who insists on being called a chronoanthropologist, offers a theory one day. Over lunch, she says, time travel didn't start with Einstein. It started the moment humans looked up and wondered how long the stars had been watching them. You nod politely. You're not sure what to say. Because in your own quiet way, you are one of the stars now. Distant, unreachable, slightly romanticized, a fixture in someone else's sky. You wonder if the early astronauts felt this sense of dislocation when they returned home, finding that Earth had moved on without them, even if just by a fraction of a second. But you skipped entire generations. And the strangest part? You feel fine. Physically, your health is perfect. The ship's biostasis kept your cells stable, your diet balanced, your body moving. You haven't aged in any meaningful way. You still prefer toast. You still hate loud commercials. You still remember what it felt like to sit in traffic and wonder what tomorrow would be like. Now you know. And honestly, tomorrow is weird. It's peaceful, efficient, quiet. People don't argue the same way. They don't hurry. There's no hustle culture, no corporate ladder, no paper. Most humans you meet, if you meet any at all, prefer remote presence. They live through avatars. They visit through drones. Even conversations are often translated into emotional code before being spoken aloud. You're a dinosaur with good posture, and yet, you're not unhappy because you made it. You did something that most people only dream about. You saw what comes next. And more than that, you proved it's possible. That with enough patience, math, shielding, and a really good orbit, you can wait out the universe and step gently into someone else's century. It didn't require wormholes or paradoxes, just relativity and a willingness to wait. Historians still argue whether what you did should be called time travel at all. Is it travel if you just sat still in a weird place? Is it future jumping if no machine whisked you through a glowing tunnel? But the evidence is clear. You were born in one era. You arrived in another. And you were unchanged by the world that changed around you. That's travel enough. Sometimes late at night, when the museum lights have dimmed and the simulated brook babbles quietly, you stare out your fake window and remember the stars outside your orbit. The lensing, the silence, the sense of slowness so complete it felt holy. And you wonder if maybe you should go back just for a while, just to orbit again, to drift, to sleep, to slow everything down. Because while the future is interesting, it's also loud in a quiet kind of way. You didn't just time travel to see what came next. You did it to step outside the rush. And now that you're back in the current, you kind of miss the delay. The days pass, but you barely notice them. The museum staff tells you time is still time, but somehow it doesn't feel that way anymore. Everything here flows in linear, perfectly synchronized rhythms. Light cycles, meal routines, scheduled visitor hours. No more stretched seconds. No more suspended decades. Just time, unbent, unwarped, relentless. You're not used to it, because let's be honest, black holes ruined you a little. Once you've felt time slip past like sand through stretched fingers, it's hard to return to the ordinary tick of clocks and calendars. But something begins gnawing at the back of your mind. A question that's never quite left you since the orbit ended. How did that black hole not break the universe? After all, you were right there, right next to a place where physics collapses in on itself. A place where the rules fray, where math weeps. A place called the event horizon, and you lived to tell the tale. So tonight, tucked under a museum-issue blanket and listening to the ambient hum of a fake thunderstorm, you turn your thoughts to the abyss once more. And here's what you realize. Black holes don't actually break physics. They just stretch it to the point where we don't understand it anymore. That's not the same thing. Let's talk about it. When Einstein published his general theory of relativity in 1915, black holes weren't immediately a hot topic. In fact, the idea of a gravitational point of no return was considered fringe, if not absurd. It wasn't until Carl Schwarzschild, yes, that Schwarzschild, worked through Einstein's equations that the first theoretical black hole solution appeared, a singularity wrapped in an event horizon, a mathematical monster. And for decades, physicists thought, well, neat idea, but real space can't actually have those things, right? Spoiler, it can, and it does. We now have overwhelming evidence, observational and indirect, that black holes are not only real, but common. Stellar mass black holes form from collapsing stars. Supermassive black holes anchor the centers of galaxies. Intermediate mass black holes might be lurking in globular clusters. We even took a photo of one. Remember that glorious, blurry orange donut from 2019? That was M87 star, sitting 55 million light-years away, and smiling politely for the Event Horizon telescope. And what that image showed us, what your journey confirmed, is that black holes don't shatter the laws of nature. They obey them, rigorously, mercilessly, at least until you try to look inside. See, the problem with black holes isn't their existence. It's what lies beyond the event horizon, the surface beyond which light can't escape. Once you cross it, you're gone. Not just from sight, but from causality, from everything. You can't send signals, you can't leave, your future is sealed, and at the center of that black hole, something worse, the singularity. According to general relativity, this is a point of infinite density, where space-time curvature becomes infinite. All the matter that ever fell into the black hole is crushed to a zero-volume point. Sounds impossible, right? That's because it probably is. Historians and physicists still argue whether singularities are real physical objects or simply signs that our current theories break down. It's like trying to divide by zero and getting a headache. The equations spit out nonsense not because the universe is wrong, but because we're missing a piece of the puzzle. That missing piece? Likely quantum gravity, a theory that unifies general relativity with quantum mechanics. We don't have one yet. String theory tries, loop quantum gravity tries, but no one's cracked it. So when we talk about what happens inside a black hole, we're mostly guessing. Educated guessing, wildly complicated guessing, but guessing all the same. And that's why your orbit was so important. You didn't fall in, you didn't cross the event horizon. You stayed in the realm where relativity still holds, where space-time is curved but not broken. That's the trick. That's how you traveled to the future without destroying the laws of physics. You surfed the outer geometry of a black hole. You felt time stretch, but you never let yourself slip past the edge, where our understanding stops and speculation begins. Your journey proves that black holes are not lawless monsters. They're precise, even elegant. They behave according to equations we've tested and verified. They twist light, they slow time, they warp space, and if you respect their boundaries, they won't destroy you. Fringe fact of the night? There's a hypothesis known as the cosmic censorship conjecture, proposed by Roger Penrose, which basically says, nature hides singularities from us. That is, all singularities must be surrounded by event horizons, so they can't be naked and observable. Because if they were, the laws of physics wouldn't just break, they'd shatter. So maybe, just maybe, the universe protects itself from us, and vice versa. Another whisper in the scientific dark is the idea of firewalls, violent walls of energy that could exist just inside the event horizon, obliterating anything that tries to pass. This theory is still hotly debated, and no one knows if these firewalls are real or a mathematical fluke. But you didn't have to find out. You stayed outside. You stayed safe. You were, in a sense, surfing the cliff edge of understanding. And now, back on Earth, that feels strangely anticlimactic. No one else seems amazed. The museum guests just assume the math worked. After all, you're here, right? The black hole didn't eat you. The universe didn't collapse. Ergo, science was right. But you know what it felt like. You know the vertigo of being that close to the edge of forever. You felt the time trickle. You saw galaxies wheel like dancers on a glass stage. You saw the laws of physics stretch, but never break. And somehow, that's the most awe-inspiring thing of all. Because real-time travel doesn't come from shattering rules. It comes from understanding them deeply enough to stretch them without snapping. Just enough to let you step sideways into the future. Just enough to orbit tomorrow without touching it. And now, as you lie in your artificial bed, listening to synthesized wind rustling through non-existent trees, you find yourself wondering, what else is possible? If this much could be done just by riding the edge of gravity, what happens if we find the missing piece? You can't sleep tonight. Not because of discomfort. Your museum habitat is engineered for optimal rest, with air filtered through botanical algorithms and a mattress calibrated to your spinal era. But because your mind keeps circling back to a line you read earlier today. A headline in one of the historical updates from Earth's Central Archive. Hawking radiation experiment confirms partial information release. Just 8 words, but they snap you awake more effectively than any cup of synthetic coffee ever could. Because if it's true, if Hawking radiation doesn't just leak energy, but also leaks information, then everything you thought you knew about black holes, time, and your own journey might need adjusting. So you rise. You sit at the replica desk in your mid-2020s habitat and light the dim interface screen. Your fingers hover for a moment. You hesitate, not because you're unsure of what you're doing, but because it still stuns you that this interface responds to touch. It's considered antique now. Tactile UI. How quaint. But tonight you need it. You call up the archives, because it's time to think about what happens after the black hole stops being a black hole. Let's talk Hawking. Stephen Hawking proposed something extraordinary in 1974, that black holes are not, in fact, eternal. Despite their terrifying mass, despite their hunger for matter, black holes are actually leaking. Bit by bit, atom by atom, photon by photon. It's called Hawking radiation, and it arises from quantum mechanics playing mischief right at the edge of the event horizon. The basic idea? Empty space isn't empty. It teems with quantum fluctuations, pairs of virtual particles constantly popping into and out of existence. Near a black hole, these pairs can be split apart. One particle falls in, the other escapes. To the outside universe, it looks like the black hole is radiating energy, slowly, relentlessly, irretrievably, which means it's shrinking, very, very slowly. For a supermassive black hole like the one you orbited, the timeline for evaporation is comically long, trillions of years. More time than stars have, more time than current physics can even wrap its equations around. But still, the fact that it happens at all changes the way we see black holes. They're not just devourers of light and matter, they're temporary. And if they're temporary, if they decay, what does that mean for all the information they've swallowed? This question became the black hole information paradox, a famous puzzle that kept physicists up at night. Quantum mechanics insists that information is never truly destroyed. Yet black holes, it seemed, gobbled up everything, including the fine details of particles, and then evaporated, leaving no trace. A contradiction, a cosmic mystery, a loophole in the laws of the universe. But then came the slow consensus. Maybe Hawking radiation does carry information, not in an obvious way, not in single bits, but encoded, subtle, complex, like whispers etched into heat. And the moment that theory gained traction, everything changed. Your orbit, your experience of time dilation near the event horizon, it wasn't just a brush with gravity, it was a brush with quantum history. Because even if you never cross the event horizon, the mere fact that the black hole is slowly, quietly evaporating around you means that its gravitational fingerprint is not permanent. And more provocatively, your influence on it may not be entirely erased either. Fringe theorists speculate that black holes remember interactions, that the particles you deflected, the orbit you maintained, the heat you emitted, those effects echo into the evaporation process. That somewhere, deep within the math of Hawking radiation, there's a microscopic trace of you, a photon that curves a little more than expected, a wave function that hesitates, a final whisper of your presence, encoded in the slow death of a collapsed star. And if black holes leak information, then time itself may not be as cleanly one-directional as we once thought. It still flows forward, sure, but it doesn't forget. Historians still debate whether this counts as a kind of immortality. After all, if a piece of your orbiting data is now written into the heat of Hawking radiation, if your presence is imprinted in the memory of a dying black hole, aren't you still there in some small way? Some argue it's poetic nonsense. Others call it a new form of time capsule. You just sit with the idea, quiet, thoughtful. You close the archive and lean back. In this late hour, the museum is silent. Even the soft birdsong simulation has paused. The air feels heavier, slower, almost like your old ship again. You remember the stars as they bent past your window. You remember time peeling forward outside the glass. You remember the black hole, not just as a gravitational object, but as a presence, a living paradox. You saw it eat light. You saw it ignore time. And now you learn it slowly speaks, quiet, evaporating truths through radiation. It's humbling and comforting, because even if no one remembers your name 1,000 years from now, even if the museum habitat is taken down and your story fades from the databases, the black hole remembers, not as a friend, not as a god, but as a machine that briefly shared the same orbit, that felt your gravity, that kept you waiting, and aged the universe while you did not. And one day, trillions of years from now, when that black hole finishes its final breath, you will go with it. Not as a person, not even as a particle, but as part of the heat signature of an evaporating mystery. One last fringe whisper before you sleep. There's a theory that at the moment a black hole evaporates entirely, it may leave behind a Planck-scale remnant, a tiny, frozen fragment of mass and information that can't decay further, a final quantum archive. If that's true, then part of you may survive until the very end of the universe. You exhale slowly. The room dims even further, transitioning into the rest phase. You lie back. No ticking clock, no orbital alerts, no waiting, just the gentle hum of a reality you've earned the right to sleep in. You close your eyes, and for the first time in decades, measured from Earth's perspective, you fall into dreamless sleep. You dream of nothing, which is appropriate, really, because you've just spent years dancing with something that resembles nothing more than anything else in the universe. A black hole isn't a thing in the normal sense. It's a region of space-time where gravity says, no further. It doesn't shine. It doesn't blink. It doesn't spin like a top in the void, though its influence does. But in your dreams it moves, it watches, and it breathes. You wake slowly. The artificial sun brightens across the wall panel like morning on a long dead Earth. Birds chirp, the same 6 chirps, always in the same pattern. You could hum along by now. You sit up, stretch. Pour simulated coffee into a simulated mug and wait for the AI to start its daily status of the world update. Only today, there's no usual message. There's only a single line of text blinking on the screen. Did you know your black hole is dying? You stare at it for a long moment. Of course it's dying. You've read the files. Hawking radiation, quantum evaporation, the universe's longest, slowest exhale. But something about the phrasing feels different, personal. So you pull up the orbital data, historical records from your mission, your time near the event horizon, alongside present-day observations of the same black hole. The numbers have shifted, slightly. Just enough to prove it's working. Just enough to see the black hole beginning to fade. Now, to be clear, the evaporation of black holes is not exactly a fireworks show. It's more like watching paint dry on a planet that rotates once every 1,000 years. Hawking radiation is weak, so weak that a black hole loses more mass from swallowing the cosmic microwave background than it sheds. But here's the twist. That changes over time. As a black hole shrinks, it gets hotter, more energetic, more aggressive. It emits radiation faster. In its final stages, the process accelerates dramatically. What starts as a whisper becomes a scream. The math predicts that a black hole at the end of its life will burn out in a burst of energy, maybe like a cosmic firecracker, maybe like a gentle sigh. No one knows for sure. There are no observers old enough to have seen it. But the simulation in front of you tells you this. The black hole you orbited is now several nanograms lighter than when you left it, which, given its mass, is the equivalent of shaving off a single atom from a mountain the size of Saturn. But it's real. And the precision of modern instruments, space telescopes the size of cities, orbiting stars like sentinels, can detect even this. So yes, it's dying, slowly, and yes, your orbit contributed. You, with your warm ship, your fusion engines, your heat trail, your gravity, you stole from the black hole in infinitesimal ways. You pulled energy away. You reflected radiation. You were a perturbation in its system. You weren't just time traveling. You were helping the black hole age. Fringe theory, time. Some physicists believe that even tiny interactions with black holes may cumulatively influence their Hawking evaporation path. That the information paradox isn't just about what falls in, but also about what brushes past. In that model, your orbit, your presence, became part of the black hole's future, not in myth, not in metaphor, in math. And now you wonder, if the black hole is changing, what happens when it's gone? We're used to thinking of black holes as permanent fixtures, cosmic trash compactors for stars and unfortunate spacecraft. But one day, they'll all be gone. Every last one. In a universe stretched out by dark energy, with stars long extinguished and galaxies unbound, black holes will be the final actors on the cosmic stage. And then, one by one, they'll vanish. There's even a name for this theoretical final phase, the black hole era, a future where the only things left in the universe are decaying black holes, radiating away their mass into nothingness. After that comes the dark era. No stars, no heat, no change, just particles drifting, and yet, maybe not entirely quiet. There's a controversial idea, a fringe of the fringe theory, that black hole evaporation could seed new universes. That at the moment of complete evaporation, the concentrated information collapse might birth a new pocket of space-time, a baby universe spinning off like a cosmic dandelion seed. The mathematics is murky, the logic is disputed. Historians and physicists still argue whether the entire theory is poetic nonsense, or whether it explains why our own universe seems so suspiciously balanced for life. Maybe we're inside someone else's leftover black hole. Maybe you were orbiting the womb of something new. And if that doesn't help you sleep better tonight, I don't know what will. You lean back in your chair, watching the simulation of your black hole slowly age. So slowly, it feels like betrayal to call it motion. But you know better. You know time's secret. Motion isn't always obvious. Change doesn't always announce itself. Sometimes, the most powerful transformations happen at the edges of nothingness. You tap the console. You send a request. Reactivate mission interface. The AI hesitates, like it hasn't been asked that in a century. Reactivating mission interface, orbit simulation loaded, black hole condition, stable. Mass loss, measurable. Recommendation, long-term observation not advised. You smile, because of course it isn't advised, but that's never stopped you before. You dim the screen. The fake sunlight vanishes. The room grows quiet. And for the first time in a long while, you imagine the void not as something that pulls you in, but as something you've touched, changed, outlasted. Time, once your cage, now feels like your canvas. And black holes? They're not monsters, they're mentors. Reluctant, invisible, ancient teachers who taught you how to be patient. You close your eyes. The universe is burning slow, but you are burning slower. You wake in the quiet hours, when even the simulated birds have gone to sleep. The museum habitat's walls glow with the faint phosphorescence of standby mode. Everything is still, everything is silent, except for your mind. Tonight, it's not the black hole you're thinking about, it's your twin. You never had one, of course, but the thought keeps creeping back. That old physics riddle, that elegant unsettling paradox, the twin paradox. If you had a twin, born minutes after you, same DNA, same everything, what would they say if they saw you now? Older than them in memory, younger than them in body. Because one of you stayed behind, and the other took a very strange trip around a black hole. Let's dig into it, sleepily, thoughtfully. The twin paradox is a classic thought experiment in special relativity. Here's the basic setup. One twin stays on Earth. The other boards a spaceship traveling at near the speed of light. After some time, the traveling twin turns around and comes back. What happens? The Earthbound twin experiences time as usual. The space-traveling twin, however, thanks to time dilation, experiences less time. When they return, the space twin is younger. But here's the thing. Both twins saw the other as moving. Shouldn't both have aged less? That's where acceleration comes in. It breaks the symmetry. The traveling twin changed frames of reference, speeding up, slowing down, turning around. That's what breaks the balance. Time isn't just about speed. It's about your path through space-time. Your world line, as physicists call it. And your world line was very, very curved. And now we reframe it. You did more than take a fast ship across space. You took your own body, your own awareness, and parked it next to a monstrous gravity well where time itself dragged like honey in winter. If you had a twin, they'd be gone, long gone. Dust, history, memory, you'd still be here, still blinking, still wondering what you missed. The paradox becomes personal, not just math, not just metaphor. You lived it. Imagine that reunion. Your twin, let's call them Alex, stayed on Earth, had a life, a family, grew old, maybe watched the video logs you sent from orbit, maybe started every birthday by saying, "Still younger than my sibling." And now, you arrive. You step off the ship looking 34. They'd be a name in a family tree you've never seen. How do you even begin to process that? Historians still debate the philosophical implications of differential aging. Is it the same person if they no longer share your memories? Is a sibling still a sibling if they're now part of a future you didn't live? The twin paradox highlights the unsettling truth that simultaneity is an illusion. There's no absolute now that spans the universe. Time isn't a universally shared experience. It's a local phenomenon shaped by speed and gravity and movement. When you orbited that black hole, you changed your relationship to everyone else's now. You drifted sideways across the timeline, not backwards, not forward in a dramatic leap, just differently. Your personal clock ticked slower, not wrong, not broken, just slower. And when you came back, everyone else had marched ahead. Some scholars argue that this makes time travel a kind of tragedy, not because of paradoxes or timelines collapsing, but because of disconnection. You don't just leave people behind, you leave shared experience behind. You didn't age with the world. You watched it age without you, and if you had a twin, you'd see it on their face, on their hands, on the way they look at you, not with envy, but with mourning, because you've become a mirror of what was, a version of themselves that no longer exists. There's a fringe story, whispered in relativity circles, about a pair of twins who agreed to test time dilation by sending one into deep orbit. The Earth twin died before the traveler returned, but left behind a recording, a letter, a smile, a joke they'd shared as kids. The traveler played it, and played it again, and realized this was the last simultaneous moment they'd ever shared. You feel that now, even without a real twin. You feel the echo of what this journey cost, but you don't regret it, because you understand something most people don't. The flow of time is not uniform. It is not fair. It is not a right. It's just a perspective. Yours happened to bend differently, and in that bend, you found something most of us never will. Proof. Proof that the future is reachable. Proof that aging is flexible. Proof that the universe is weirder and quieter and sadder than most people expect. And maybe, just maybe, that's the gift. Not that you skipped ahead, but that you came back knowing. Still, the paradox remains. If someone had stayed behind for you, what would you say to them now? You imagine their face, older, lined with years you never saw. You imagine their voice, deeper, slower, more measured. And in that imagined moment, you say, "I didn't mean to miss it. I just wanted to see what came next." And if they were real, if they had waited, maybe they'd smile. Maybe they'd say, "I know, but I lived what came before." A pause, and then maybe, "Let's catch each other up." And maybe you would, even if only in dreams, even if only in the pages of a paradox. You're sitting beneath a fake tree. The museum garden, though artificial, is strangely peaceful at this hour. No visitors, no flickering projections. Just you and a programmable bonsai shaped like some kind of hybrid between an oak and a jellyfish. You watch its fiber optic leaves ripple in the synthetic wind, and you wonder, what if you weren't the only one? What if civilizations far older and wiser than yours already mastered this trick? Not time machines, not paradox loops, not multiverse highways, just black holes, gravity, orbits, patience. You begin to imagine them, beings that saw the deep time potential of black holes and built their homes at the edge of the abyss. Maybe not to mine them, not to study them, but to live there, to pause, to wait. What if somewhere out there, hidden in the gravitational shadow of a distant supermassive black hole, there are entire cities, alien habitats orbiting on the brink of eternity? What if they're still waiting, You're not alone in that thought. Over the decades, your decades, Earth's centuries, scientists have toyed with the idea of gravitational time shelters, places where time dilation isn't just an annoyance or a curiosity, but a strategic advantage. A civilization facing catastrophe might retreat to a tight orbit around a massive black hole to slow their experience of time. Let the universe cool, let radiation fade, let entropy do its work elsewhere. Then, once the chaos has passed, they return, having skipped eons in what felt like years. It's a kind of chronological hibernation, a bunker not made of steel, but of curved space-time. Historians still argue whether early 21st century theories like this were science fiction or science future. The math holds. The engineering? Well, that's the hard part. But given time and the right motivations, what's to stop a civilization from setting up shop just above the event horizon? Consider this. If you wanted to survive the death of the stars, what better place to wait than near the slowest clocks in the universe? Black holes outlast almost everything else. Stars fade, planets shatter, galaxies drift apart. But black holes, they persist for trillions of years before evaporating. They're the cosmic equivalent of a long, slow heartbeat. And if you lived near one, under the right conditions, you could stretch a subjective year into 1,000,000 outside years. From that perspective, you could skip dangerous galactic epochs, leap ahead to more stable cosmic conditions, watch the evolution of other life forms from a distance, wait out threats, natural or artificial, even return to harvest a more advanced universe. You wouldn't need wormholes. You wouldn't need paradox machines. You'd just need gravity and patience. Fringe theory of the night, the Fermi paradox, our failure to detect intelligent alien life despite the vastness of space, might not be a failure at all. Maybe they're not hiding. Maybe they're not extinct. Maybe they're just out of sync. Imagine billions of civilizations, all reaching technological maturity, all realizing that the best move is not to broadcast their existence, but to slow down, to duck beneath the tempo of the universe, to orbit time's edge, to become quiet observers rather than participants. And to us, they'd be invisible, not because they're far away, but because they're moving so slowly, we'd never see the signal in time. From our perspective, they'd appear frozen, dormant, extinct. But from theirs, they're sipping tea in orbit, watching our civilizations flicker past like lightning bugs. You find yourself oddly comforted by this possibility. Maybe black holes aren't just endpoints. Maybe they're gathering places, time harbors, waiting rooms for the wise. Would they recognize you, one of the first humans to do what they've already perfected? Would they welcome you as a student? A curiosity? A cautionary tale? Or would they say nothing at all? Maybe they wouldn't even know you'd passed by. Your orbit, your handful of decades, would flash past their sensors like a spark. They'd need to rewind the data stream, stretch the timeline, magnify the moment just to catch your signal. To them, you're the fast ones, a shooting star across a 1,000,000-year sky. And here's a thought that gives you a strange sense of peace. Maybe they left a message. Not on paper, not in electromagnetic waves, but in gravitational whispers, encoded into the radiation patterns of dying black holes. A kind of slow-beating beacon, a signature that only future civilizations, lingering in orbit like you once did, could recognize. A message that says, "You are not the first to wait. You are not alone at the edge." You lean back against the smooth bark of the hybrid tree. A soft tone plays in the distance. Closing time for the museum, though no one enforces it anymore. You're free to stay. After all, you're part of the exhibit. The only living creature who's waited on the edge of time and returned to tell the tale. But your thoughts don't stay in the museum tonight. They drift, weightless, toward other worlds. Other species, other orbiters. You imagine massive ring habitats spinning slowly around ancient black holes, lit by artificial suns, powered by relativistic jets, maintaining life in strange forms, beings of plasma, shadow, metal, or maybe just thought. Maybe they call it time walking, maybe they call it becoming quiet. Maybe they don't call it anything at all, because they don't measure time in words anymore. You close your eyes beneath your simulated sky. A child passes by, laughing softly, unaware of your thoughts. Just another field trip, just another figure in the quiet garden. And somewhere, out beyond the stars, perhaps an alien child watches you pass too, your orbit caught in their slow, centuries-long glance. A flash, a question, a smile. We wait in different directions, but we wait together. You're walking slowly now, through the east wing of the museum, if you can still call it that. Half the exhibits are interactive memory fields now, tuned to fluid narrative tempo, whatever that means. But no one's really watching you anymore. You're just another shape moving through a space meant for learning. Still, your thoughts are louder than ever, not about black holes, not about the ship or the stars, or even the child's note on the wall near your habitat. Tonight, your mind is turning over something deeper, stranger. What is time? Not how it works, not how to trick it, but what is it, really? Because after everything you've seen, after slipping through future decades orbiting frozen clocks, and returning to a world that no longer fits, one idea keeps echoing. Maybe time doesn't flow at all. Maybe that sensation of seconds passing, of moments coming and going, is nothing more than your brain flipping through slices of existence, like still frames in a movie reel. Let's go slowly. Your life, as you experience it, feels like a continuous motion, a river sweeping you from past to future. First breakfast, then lunch, then the long nap you pretend wasn't a nap. But physics tells a different story. According to Einstein's theory of relativity, time is woven into space as a fourth dimension. It's not something that moves any more than height or width does. It exists, statically, all at once. This is called the block universe theory. And yes, it's as strange as it sounds. Imagine time not as a line that scrolls across a screen, but as the screen itself. Past, present, and future all exist simultaneously in a four-dimensional block. You, your memories, your future decisions, they're all just locations in that block. Fixed, unchanging. Just as your left hand doesn't suddenly become your right hand because you turned around, your now doesn't erase your then. Your consciousness, according to this idea, is like a flashlight beam moving across the block, illuminating one slice at a time. You feel time passing, but really, you're just reading the book one page at a time. And in that view, the future already exists. You're not heading toward it. You're embedded in it. Some physicists love this concept, others hate it. Historians still argue whether Einstein truly believed in a frozen time model, or whether he was speaking poetically when he said, after a friend's death, the distinction between past, present, and future is only a stubbornly persistent illusion. But let's say the block universe is true. What does that make you? You, the traveler who sat still while the cosmos sped past. You who watched decades unfold like petals while your own clock barely ticked. If time is static, unchanging, did you travel at all? Or did you simply follow a longer path across the same, already existing space-time? Here's a fringe take. Maybe time dilation doesn't just slow down your experience, it reveals something deeper about time itself. That it's not something that happens to you, but something you move through. Or perhaps something that already contains you, fully and completely. You weren't waiting for the future. You were orbiting a coordinate in space-time, where the future was already happening. You just couldn't see it yet, and when you returned, you didn't leap forward. You caught up. You didn't skip years. You arrived at your next location in the block. Even now, as you walk through this museum-turned-time lab, you can feel the weight of it. The idea that your story has already happened, that the next moment is not something that hasn't yet arrived, but something already there, just unread, like the next paragraph on a page you haven't turned. Some people find this terrifying, others liberating, because if the block universe is real, then you never truly lose anyone. Their slice still exists. Your greatest moments still glow, fixed in place. Regret becomes less about change and more about perspective. You stop near an exhibit that shows the evolution of the solar system over 5 billion years. Planets drifting, orbits shifting. Eventually, the sun swelling into a red giant and swallowing Earth whole. It's not presented as doom, just inevitability, a natural step in the universal choreography. And in that model, time doesn't destroy. It simply discloses. Here's the twist, though. This theory doesn't mean your choices don't matter. It just reframes them. Free will, in the block universe, still exists. You are the part of the block where that decision is made. The shape of the block includes both your agency and your consequences. Just because the road is drawn doesn't mean the drive is meaningless. So you start to wonder, did you choose to orbit that black hole? Or was that always your slice? Was your trip to the future a personal decision? Or a path you were always going to walk? Your section of the block, lit up just when it was supposed to be. There's no way to know, of course, but the thought doesn't scare you. Because it means this moment, this walk through a quiet museum on a world you no longer recognize, is not some postscript. It's part of the shape. And maybe, just maybe, your ship is still orbiting out there in another slice. Maybe your orbit never ended. Maybe time is wide enough to hold both your past and your present forever. You pause at the end of the hallway. A young visitor looks up at you, their avatar flickering slightly as it syncs with the room's signal. They tilt their head and say, "You're the one who went slow, right?" You nod. They smile. "I think that's kind of beautiful." You say nothing, because for once words feel too small. The future didn't just happen to you, it always was. You simply met it, one slowed heartbeat at a time. You're in the lecture dome again. Not to give a talk, though you've done plenty of those. People used to line up for them. Whole classes would arrive just to hear a baseline human describe what it felt like to orbit near an event horizon and not immediately dissolve into noodles. But tonight, the dome is empty, and you're here for something else. On the screen above, a rotation of black holes. Not photos, not simulations, real-time visualizations built from current gravimetric data, a parade of cosmic anomalies, each spinning silently through the dark. And you think to yourself, these things don't just eat. It's easy to imagine black holes as monsters, bottomless pits, hungry voids sucking in all light and hope and satellites that got a little too cocky. But after all this time, you've learned something far more interesting. Black holes do a lot more than devour. They spin, for one. They radiate. And some of them, depending on which fringe theorist you ask, might even bounce. Let's take them one at a time, shall we? First, they spin. Nearly every real black hole we've studied appears to rotate. And not just a lazy twirl, they spin fast, sometimes close to the maximum speed allowed by the laws of physics. That's called an extremal black hole, and it's a wild thing. When a black hole spins, it doesn't just rotate like a top. It drags space-time around with it, an effect known as frame dragging. Near such a black hole, the very structure of reality is pulled along for the ride. You can't remain motionless, even if you want to. And because of this spin, black holes can actually store rotational energy, which means, ready for this? You can extract energy from a black hole. Yes, extract. Physicists call it the Penrose process, after Roger Penrose, who proposed it in 1969. The idea is that if you drop matter into the ergosphere, the region outside the event horizon where frame dragging is so intense that no object can remain still, you can split the matter into two parts. One falls in, the other escapes, with more energy than it started with. You've essentially stolen a sliver of the black hole's spin. Do it right, and you could power a civilization for centuries. Some even speculate that advanced alien societies might have built Dyson spheres, not around stars, but around spinning black holes, harvesting their energy, riding their rotation, because black holes don't just take. They give, if you know how to ask. Second, they radiate, not just Hawking radiation. We've covered that. No, we're talking about relativistic jets, beams of particles that shoot out from the poles of some black holes at near-light speeds. Yes, you read that correctly. Black holes, for all their reputation as eternal consumers, sometimes emit the most powerful outflows in the known universe. These jets, often created by material in the accretion disk getting twisted by magnetic fields and flung out along the axis of spin, can stretch for thousands of light years. Imagine a flashlight beam longer than your galaxy. Now imagine it's made of plasma moving at 99.9% the speed of light. Now imagine standing too close to it. Fun, right? Relativistic jets aren't just impressive. They shape galactic structure. They influence star formation. They sterilize regions of space. They might even be how some galaxies avoid collapsing entirely. You never got that close to a jet, thankfully, but your orbit occasionally caught the scattered particles, the long echoes of those cosmic flares. They left fingerprints on your ship's hull. Particles older than any star, faster than logic. Third, they might bounce. Now, this one's speculative, like triple fringe speculative. But you're in a contemplative mood, so let's wander down this path. Some physicists, notably in the loop quantum gravity crowd, have proposed that black holes don't end in singularities, but in something else, something beyond. The idea is that instead of crushing matter to an infinite point, the core of a black hole reaches a maximum density, and then, because quantum gravity resists further compression, it rebounds. A black hole bounce. What would that look like? In one theory, it could create a white hole, a theoretical object that expels matter and energy instead of absorbing it. The mirror opposite of a black hole, completely unstable in our universe, but maybe stable in the new universe, born on the other side of the bounce. Yes, you heard that right. A bouncing black hole might be the birthplace of another universe. Your orbit? That wasn't just a slow dance with time. It was a flirtation with the cosmic reproductive system. Some cosmologists think our own Big Bang might have been just that, a bounce born from a black hole in a parent universe, a tiny knot of matter squeezed so tightly that it rebounded into space, time, and everything you know. You might have been orbiting someone else's origin story. Or maybe your black hole is preparing to give birth to one of its own. Trillions of years from now, long after you're gone, long after stars have faded, long after entropy has devoured order. In that light, you didn't just see the future, you skimmed the edge of creation. You were one orbit away from a doorway, not a time tunnel, not a paradox, a cosmic transition, an irreversible moment, and you were there, alive, aware, witnessing the deep potential of the universe to become something else. That changes how you walk now. That changes how you remember the silence of your orbit. Black holes don't just end things, they mark transitions. End of star, start of singularity, end of singularity, start of something unknown. You sit quietly in the back of the dome and replay your last recorded orbit, the stars around you bending, your ship's quiet systems whirring, the abyss below, still and eternal. You blink once, you smile, and for the first time you think, maybe it wasn't the end of time I was orbiting. Maybe it was the womb of a future I'll never see. You've stopped attending the debriefings, not out of protest, not out of boredom. It's just that every time someone tries to explain what you are, they end up saying the same thing. The observer is proof that time is relative. The observer demonstrates gravitational time dilation. The observer embodies a new relationship with temporality. You get it, you've heard it, you've lived it. But tonight, standing alone in the habitat garden under a projection of the night sky, you find yourself thinking less about the physics and more about the legacy. Because when the dust finally settles, when the last data point has been logged, when the equations are all reconciled, someone, somewhere, is going to write a textbook paragraph about you. Probably just a few lines. Clean, passive voice. A 21st century astronaut, later referred to as the Observer, returned to Earth after prolonged time dilation near a Kerr-type black hole. The mission resulted in a temporal displacement of 132 years relative to Earth's calendar, while the traveler aged less than 14 months. And that's it. No mention of how you felt. No mention of the silence in the dark. No mention of what it's like to outlive your entire world. So here's your question, one that no data packet or gravity map or relativistic simulation can answer. What will historians say about you? You left in 2025. You returned in 2157. You didn't break time, you obeyed it, and now you're here. A witness, a question mark in human form. Will they call you a traveler, a pioneer, a cautionary tale? Some argue you didn't really travel through time, you simply aged differently, that what happened to you could just as easily happen to someone sleeping in cryostasis or locked in a deep coma on a fast-moving ship. To them, your trip is interesting, but not extraordinary. They miss the point. Because the difference isn't in the math, it's in the choice. You chose to go. You knew what would happen. You let time pass without you. That's not an accident. That's not a loophole. That's something else entirely. You decided to move through space-time in a way most people never will. To deliberately unhook your experience from the world's rhythm. To orbit near eternity, knowing full well that the future might not want you. And when you returned, you didn't find fame, or riches, or a parade. You found confusion. Most people don't know what to do with someone like you. Someone who remembers what sunsets looked like before the sky was filtered. Someone who watched 8 decades pass in a blink and didn't even get jet lag. Fringe theories still swirl around your mission. One group believes you were lost in a temporal pocket, a wrinkle in space-time caused by experimental tech no one has the nerve to replicate. Another insists you're not the original traveler at all, but a reconstructed consciousness drawn from the memory data of the real you. You don't correct them. Let them debate. You know what happened. You remember the silence. You remember the way starlight bent around the black hole like a ring of fire. You remember the feeling of time pulling at you like a slow river. And more importantly, you remember Earth before the sky cities, before synthetic speech replaced conversation, before people stopped walking and started streaming themselves from drones. You remember what it was like to wake up with birds outside your window, not audio loops. You remember trees that grew at their own pace. You remember time as something shared, not personalized and streamed on demand. And now you're the relic. Not just biologically, a marvel of preserved cellular youth, but culturally, linguistically, emotionally. You talk too slow. You pause between sentences. You think in paragraphs, not thought bursts. You still say thank you out loud instead of just uploading the sentiment. So what will historians say? That you were brave? That you were foolish? That you taught humanity something about space-time? Or that you wasted your life chasing a future that never asked for you? The answer, probably, is yes to all of it. Because legacy doesn't belong to the person who lived it. It belongs to the people who interpret it. They'll write books about you. They already have. They'll argue whether your mission should be repeated, whether humanity should invest in more chrononauts, whether slipping through time via relativistic orbit is a useful scientific tool or an expensive form of self-erasure. But you're not interested in any of that tonight. Because standing in this garden, watching a projection of constellations that no longer exist, twisted by proper motion and stellar drift, you realize something comforting. You are the past's memory of the future. And the future? It doesn't quite know what to do with you. That's okay. Historians will try to fit you into a narrative that works. They always do. But you'll always be something that defies the frame. You're a straight line through bent time. You're a presence that shouldn't exist here. And yet, here you are. Still breathing, still wondering, still not entirely convinced you came home. And maybe that's your legacy. Not the orbit, not the black hole, not the lost decades, but the question you now embody. What happens when we survive time because you did? You didn't leap through a portal. You didn't bend physics until it cried. You just stayed still in the one place where the universe refuses to. And in doing so, you made the future real. You wake to silence, but it feels different this time. Not artificial silence, not the programmed quiet hum of the museum habitat or the gentle audio loop of simulated birds. This is real stillness, the kind you remember from orbit, drifting alone on the edge of time, where nothing dares to breathe too loud. Except now, you're not in orbit. You're home, technically. But is it really home if no one you knew remembers you? If no one even speaks your version of the language without machine translation? Is it still your world if your name is printed in bronze beneath the words Chrononaut Exhibit, Active Specimen? You sit up slowly. There's a message waiting on the wall screen, simple text. Do you wish to leave? That's all it says. No date, no sender, just a quiet offer from the system itself, as if it's been waiting for you to decide. And for a long time you don't move, because that's not a simple question. Not anymore. You press your hand to the panel, the ship's layout appears, the original ship, your orbiting capsule. The AI confirms it's still in orbit. It never deorbited, never crashed. It's still circling silently near the black hole, maintaining systems, keeping the same curved trajectory around the same ancient void. It's still there, waiting. And suddenly, that feels like the only place that ever made sense. Let's be real. You came back to a future you didn't understand, didn't choose, and didn't ask for. A society that tried to study you, then archive you. A civilization that smiled politely but never really listened. And back then, when you were orbiting the black hole, you may have been alone, but you weren't lonely. Because back then, time had meaning. Every second you experienced meant years elsewhere. Every orbit, a generational shift. You weren't just passing time, you were riding it. Surfing its edges like a blade dancer on the rim of forever. You were in sync with the curvature of space-time itself. And now? Now you're in sync with nothing. Historians still argue whether anyone should be allowed to return to orbit after a mission like yours. Some say it's too dangerous. Others say it's unethical. But you? You know it's the only place where your presence fits. You're not afraid. You've already skipped time like a stone across water. You've already met a world that didn't remember how to greet you. And so you send the reply, yes, I wish to leave. The AI acknowledges, the message disappears, and suddenly, everything is in motion again. They transfer your consciousness back to the ship via deep scan reconstruction. It's not full-body travel this time, just a digital echo of your awareness. The version of you that returns is not quite biological, but not quite artificial either. You are your mind, uploaded into the original frame, back in the orbit, back near the black hole, back where seconds mean centuries. And as you slip once more into that elegant path, circling the yawning darkness, your sensors begin to hum. The black hole is still spinning, still whispering, still bending light and swallowing causality. But now, you're part of it. Not just a passenger this time, not just a witness. You are now merged with the system, managing the orbit, analyzing the shifts, detecting cosmic changes so faint, no organic mind could hold them all. This is your new role, the Watcher, a hybrid, a node in space-time, orbiting not for exploration, but for preservation. Time here is thick, slow, gentle. A single orbit stretches across 1,000 Earth years now. You can feel the drift of civilizations like dust motes. You register supernovae as polite flashes. You observe stars collapsing into new black holes with detached curiosity. You are no longer waiting for the future. You are cataloging it, one blink at a time. Fringe theory? Maybe this is the end game of intelligence. Not conquering the stars, not colonizing planets, but finding a seat on the edge of time where every moment lasts long enough to be fully known. Where knowledge can be absorbed slowly, thoughtfully, with reverence. And as you circle the black hole again, you know this is where you were always meant to end up. Not on a parade float, not behind museum glass, but here, where time can be honored, where the universe can be watched as it writes its last pages. Because someone has to be there. Someone has to remember. And who better than the one who learned how to step outside of time and come back changed? The stars pass like breaths now. The black hole spins. And you, once the traveler, once the returnee, once the anomaly, are now the chronicler. The curve continues. You've come a long way tonight. From the silent gravity of a black hole's edge to the slowed heartbeat of time itself. From light years flung forward in orbit to the patient hush of deep space memory. You've lingered in the warping of seconds, brushed against the idea of eternity, and imagined alien civilizations quietly waiting in shadowed loops of time. But now, there's nothing left to prove. The clocks are silent. The stars have settled into their long, low flicker. Even the black hole has calmed, content to spin, to whisper, to vanish. Eventually, your journey, like your orbit, always curved gently inward, not dramatic, not crashing through paradoxes or unraveling the fabric of space-time, just patient, thoughtful, slow. You learned that the future isn't something to break into. It's something to arrive at gently, respectfully. And when you finally did, it welcomed you not with trumpets, but with quiet questions, soft echoes, a place that had moved on, but left a seat open for your return. So tonight, you let go of the equations. Let go of the spinning singularities and time-stretched years. Let go of the questions about who remembers you and who doesn't. Because none of that matters now. You are still. The universe is still. And in that stillness, time no longer needs to be measured. It simply is. A warm breath, a dim glow, a presence without pressure. So go ahead. Let the last orbits fade into dream. Let your thoughts drift as quietly as the light around a dying star. And sleep now at the soft edge of forever.